All right, let's resume our morning session. And our third speaker is Kohei Schmitz from CERN, and he is going to talk about gravitational waves from cosmological B-arrow breaking. Yeah, please go ahead.
Right. Okay. So, hi everybody. Thank you very much for having me today. It's a pleasure to be with you today, although only virtually and not in person, as I would have certainly preferred. And yeah, so thank you very much for the invitation. And in this talk, I will speak about gravitational waves from the spontaneous breaking of a particular symmetry in the early universe. And that symmetry is associated with B minus L, where B stands for barrier number B and L is lepton number. And the charge associated with the symmetry that I'm interested in is the difference of B and L. Okay, so this talk is based on work and collaboration with several people. You see a list of names here, people in Heidelberg, people that at the time used to be at Daisy in Hamburg, and also Hitoshi Murayama in Berkeley. And we've written a couple of papers on this topic, and you can find them on the archive. Right, okay, so let's get right into it. Here's the outline of my talk. First of all, I will introduce gravitational waves as a new probe, as a new observational window onto the famous seesaw mechanism. And then the main part of the talk will be basically divided into two sections. In the first, slightly shorter part, I will talk about gravitational waves from a first order phase transition. And then in the second, slightly longer part, I will talk about the network of cosmic strings that can be generated during such a phase transition in the early universe. And I will talk about the gravitational wave spectrum that could be emitted by such a cosmic string network. And then finally, I will conclude. So let's get started. Gravitational waves as a new probe of the seesaw mechanism. And I would like to start with this picture here that basically shows a periodic table of all the elementary particles in the standard model. And now let us all look at this table and think about the following question. So what do you think would be promising candidates for new particles beyond the standard model? And you may have your own favorite type of new particle, the axion, or some kind of WIMP dark matter particle. But I think what's particularly interesting and curious about this periodic table here is that all the standard model fermions come in pairs of left-handed and right-handed fermions, except for the neutrinos, and they only appear in the left-handed version or variant in the standard model. So what would be more natural than just supplementing this particle content by right-handed neutrinos that you arrive at such a picture here on the right-hand side? And this is not only very beautiful, but it's also actually very well motivated from a physics perspective. And yeah, such right-handed neutrinos, they may play an important role in a countless number in a variety of phenomena and scenarios of physics beyond the standard model. Right-handed neutrinos may explain neutrino flavor oscillations. They may be responsible for baryogenesis via leptogenesis. They can play an important role in grand unified theories. Recently, people talked about the idea that radiative threshold corrections from right-handed neutrinos could actually generate the mass parameter of the Higgs boson in the standard model. I don't have time to talk about this in more detail, but that's an interesting idea that goes by the name of the neutrino option. And then finally, for instance, if you've got a stereo neutrino with a mass at the keV scale, this could be an interesting dark matter candidate. Okay, so let me focus on the aspects that are most interesting and most relevant for my own work, and that is the standard type 1 seesaw mechanism in leptogenesis. So this extension of the standard model is based on the idea to introduce a set of right-handed neutrinos, okay? And then if you look at the quantum numbers of those right-handed neutrinos, you realize that, well, they're all singlets, they're sterile, they don't carry any standard model gauge interactions. So what this allows you to do is to actually write down Majorana mass terms for those neutrinos, which means that they can be Majorana fermions, i.e. their own antiparticles. And then, well, once you've written down those Majorana mass terms and you carve interactions with the leptons and Higgs doublets in the standard model, you have basically arrived at the type 1 seesaw mechanism. In the type 1 seesaw mechanism, the first diagram here on the left-hand side basically represents how you generate masses for the light neutrinos in the standard model. So I've got this heavy neutrino in the intermediate state, and then once I put the Higgs field H to its vacuum expectation value, I generate Majorana masses for the light standard model neutrinos. Similarly, I can look at the other diagrams here on this slide, and then they represent the decay of heavy neutrinos in the early universe. And if that happens out of equilibrium, the CP violation and lepton number violation in those heavy neutrino decays can actually generate a BAU, a baryon asymmetry of the universe, a primordial first lepton asymmetry and then baryon asymmetry in the early universe. So that's basically the main motivation, neutrino masses and leptogenesis for introducing heavy neutrinos. Now, once you've gone that step, you can go further and ask the next question. We just introduced those right-handed neutrino masses, Mi, for our heavy neutrinos, and then you would like to know, where do they actually come from? Can I embed my seesaw mechanism into a UV completion that explains the origin of those input parameters? And then one interesting possibility is just to consider basically a second Higgs mechanism in this heavy neutrino sector. So maybe, yeah, let's go back one step and then have a look at the global symmetries of this standard model. It turns out that baryon number B and lepton number L are global symmetries of the standard model Lagrangian. Both are violated at the quantum level by non-perturbative effects, but the difference is anomaly free in the standard model. Now, if I write down these mass terms for the heavy neutrinos, those explicitly violate lepton number L, okay? But this lends itself to this idea that the Majorana mass terms could be actually dynamically generated if B minus L is a good gauge symmetry at high energies that at some point gets spontaneously broken. So basically that's the idea here, that we promote B minus L to a local gauge symmetry, then we spontaneously break it, and that generates the Majorana mass terms in the seesaw mechanism. Now that gives us a self-consistent picture. Once we introduce those heavy neutrinos, also the B minus L gauge anomaly itself gets cancelled as long as we introduce 3 right-handed neutrinos, so that's self-consistent. And this particular combination, B minus L, or U1B minus L, also plays an important role in many scenarios of grand unification. And just to give you one example, take one family of standard model fermions, add one right-handed neutrino, that gives you already a 16-dimensional spinor representation of SO10, something that nicely fits into this framework of SO10 unification. Okay, now, once you've proposed this idea, the next natural question is to ask, well, how do we go about and discover those right-handed neutrinos? How do we find them in experiments? And for that, I'm showing here on the left-hand side an overview of the sensitivities of a couple of current and ongoing experiments that search for long-lived particles. Experiments such as Methuselah and Phaser, Codex B, SHIP, and so on. And you see that those experiments, they can probe heavy neutrinos with a mass of the order of 1 GeV or maybe 10 GeV. And then, well, for a certain range of mixing parameters. I mean, here on the vertical axis, there's a quantity that quantifies the mixing between the sterile and the active neutrinos. Okay, but how does this compare to our theoretical expectation? And for that, we can have a look at the plot on the right-hand side. And here I show the viable parameter space from the perspective of the simplest version of leptogenesis, vanilla leptogenesis. There is some kind of effective neutrino mass on the horizontal axis, and there's the heavy neutrino mass M1 on the vertical axis. And you see that in this yellow region where I can realize a successful leptogenesis, my neutrino needs to be very, very heavy, something of the order of 10 to the 9 or 10 to the 10 GeV. Certainly many orders of magnitude above those masses that I can probe in terrestrial experiments. And it's not difficult to see where this comes from. So for that, let's have a look at the formula down here. That's the mass relation, the seesaw mass formula for the masses of the light neutrinos in the standard model. The overall scale is fixed by the measured mass squared differences of neutrinos in the standard model. And then so from this relation, I see that if I want to make the neutrinos very light so that they could show up in terrestrial experiments, at the same time, they also need to be very weakly coupled. Or if I make them more strongly coupled, I also have to make them heavier so that they, again, escape detection in experiments. So it's very hard to probe the seesaw parameter space. And the question I want to ask for this talk here is, can we think of other probes of the seesaw parameter, the seesaw model and the wide neutrinos apart from those lab experiments? And for the purposes of this talk, my answer is going to be gravitational waves! Exclamation mark. So the question is, to what extent will we be able to probe the seesaw mechanism and right-hand neutrinos based on gravitational waves? Now, just a very brief overview of the current and future situation in gravitational wave astronomy. We already had very nice overview talks on this yesterday, so I can be brief here. I think it's fair to say the best is still to come. There will be new laser interferometers on the ground, such as Cosmic Explorer and Einstein Telescope. You could also do atom interferometry on the ground. They're the Ian and Major's proposals. And then the next step would be to go to space and do laser interferometry, or maybe also atom interferometry. In space, there's LISA, that's the most mature proposal, a space-based interferometer that will hopefully be launched in the next decade. And then also more futuristic proposals such as the Big Bang Observer, BBO, and DeCygo. Right, okay, and then there's the proposal of a space-based atom interferometer, and then Chinese proposals for space-based laser interferometers. And the third frontier to look for gravitational waves would be the sky. You can construct an array of millisecond pulses in the sky to basically construct a virtual gravitational wave interferometer that's as big as the entire galaxy. And there are existing collaborations already, such as the International Pulsar Timing Array, IPTA collaboration, but also future experiments such as SKA, the Square Kilometer Array, will be able to set up a PTA, a pulsar timing array, and look for gravitational waves in the sky. Okay, so for the purposes of this talk, and also, well, in my work in general, I'm particularly interested in gravitational waves from the early universe, and we also had a nice overview talk on this yesterday already. The main three sources are maybe gravitational waves from cosmic inflation. We heard about this yesterday, and I will not talk about this today. But then there are also there's the hope to see gravitational waves from cosmological phase transitions. That's something I will talk about today. And then those phase transitions, they could lead to the production of topological defects, such as cosmic strings, for instance. And I will also talk about gravitational waves from cosmic strings today. So I think the stage is set, and now it's time for me to present to you today's drink of the day. As I try to motivate, it's interesting to look at the UV completion of the seesaw mechanism based on a gauged U1 B minus L symmetry that's motivated from the perspective of grand unification, and it's a self-consistent scenario where all anomalies are cancelled. And we're going to assume that this gauge symmetry is thermally restored after inflation. So we assume that the reading temperature is high enough so that B minus L, U1 B minus L is a good symmetry in the early universe after inflation. And well, this implies that at some point later during the radiation-dominated era, during the hot Big Bang, the symmetry gets spontaneously broken. So there will be a cosmological phase transition during the hot Big Bang that spontaneously breaks U1 B minus L. Now, such a phase transition can, for instance, proceed, well, it could be a first order phase transition. And in this case, we have to look at the, well, second plot from the left down here. I think you don't see my cursor, that's why I have to describe it in words. And then in the case of a first order phase transition, the order parameter, the scalar field that breaks the symmetry, is first located in the false vacuum at the origin. The false vacuum becomes supercooled, and that's basically also what you see on the left-hand side here in this picture of this martini cocktail. Yeah, so that belongs to a recipe that allows you to prepare the world's coolest martini because you use the supercooled water to actually get the ice in your cocktail glass with which you want to cool your martini. So the supercooled phase suddenly turns, transitions into the true vacuum, into the new phase, and in this case would be solid ice. Then the symmetry is broken. The second possibility is that the order parameter, the scalar field, just evolves continuously. This would be a second order phase transition. In the first case, you could hope to see gravitational waves from vacuum, bubbles, sound waves, and turbulence. I will talk about this in a minute. And in either case, because you break a U1 symmetry, you expect to produce cosmic strings. I will also talk about cosmic strings, and then you could hope to see gravitational waves emitted by the network of cosmic strings. But first things first, let's start with gravitational waves from a first order phase transition. And here, just to set the stage, I'm showing to you a typical gravitational wave spectrum from a first order phase transition. This is not related to B minus L breaking. This is a particular benchmark point and the scalar singlet extension of the standard model. I have taken this benchmark point from the paper by the LISA Cosmology Working Group on gravitational waves from phase transitions. And I just take this parameter point. It's already a bit outdated, but still it illustrates the main point that in principle there can be three contributions to the signal. One contribution is from scalar field gradients. That's basically just the bubble walls that separate the true vacuum from the false vacuum. And once those bubbles collide, they can produce gravitational waves. But nowadays, by now it has been realized that this signal is very often subdominant. Okay, and more importantly, one has to consider the energy that goes into the motion of the bulk plasma. Initially, you will just have compressional modes in the bulk plasma. That means sound waves, and those sound waves, they can generate gravitational waves. And at some point, the motion of the plasma becomes turbulent, and then magneto-hydrodynamic turbulence will also lead to gravitational waves. That's very interesting and potentially an important source of gravitational waves, but at present, it's not as well understood and cannot be as well simulated on the computer as gravitational wave production from sound waves. Okay, just a quick overview of the important parameters that you need to calculate to come up with a prediction of the gravitational wave spectrum. First of all, there's the parameter alpha that quantifies the strength of the phase transition, and it's given by the change in the trace of the energy momentum tensor across the phase transition in units of the radiation energy density. Okay. The second parameter is beta, which quantifies, which is a measure for the inverse duration of the phase transition, and that's given by the time derivative of the Euclidean bounds action. And that Euclidean bounds action basically describes the bound solution, the bubbles of the true vacuum that nucleate in the ambient plasma. Okay. A third important parameter is the temperature scale of the phase transition, and then there is the velocity VW of the bubble walls. Now, on the previous slide, I already said that the signal from bubble collisions very often is subdominant, and the signal from turbulence very often is not as well understood. So for that reason, here I'm just showing to you the estimates of the peak frequency and the peak amplitude for the signal from sound waves. Okay, and you see how this can be parameterized in terms of those input parameters up here. Okay, and then, well, the general shape of the spectrum is supposed to be a peak where you reach a global or local maximum at this peak frequency. But then around this peak, the spectrum can be parameterized in terms of a broken power law, typically. And then this is what I show here. This is captured by this shape function S. That's basically just a broken power law. At low frequencies, this goes like f to the power p. And at high frequencies, this goes like f to the power minus q. Okay. And the standard value is also used by the LISA Cosmology Working Group. P equals 3 and q equals 4. And then this parameter n quantifies basically the width of the peak around the peak frequency. Okay. I think an important message I want to send here is that if you hope to see a gravitational wave signal from a phase transition, maybe a B minus L breaking phase transition in LISA, then that puts you into a certain part of the parameter space, and then you would think that you could only see a signal if the transition temperature is of the order of 100 GeV or maybe 1 TeV. But certainly you will not be able to see a signal if the phase transition takes place at much, much higher energies, because then the signal would move to much higher frequencies out of the sensitivity range of those experiments. Okay, maybe also just a quick comment again on this plot up here. What you see here is the prediction of the gravitational wave spectrum and sensitivity curves of those future experiments or next stages of the LIGO experiment. There are a couple of things to say on this. First of all, those Power law integrated sensitivity curves, they just give a rough impression of those experimental sensitivities. They are only exactly valid if the signal is a pure power law. That's certainly not the case here. A second point is that in those plots, it's very hard to compare a large number of spectra, because if I plot 10 spectra or 100 spectra, it becomes very messy. That's why I propose a different way of visualizing the sensitivity of those future experiments. Let me just take 1 minute to advertise this plot here that came out last week on the archive, so you can find it here in this paper on the archive. What I basically propose is to project the sensitivity of experiments like LISA into this two-dimensional parameter space that's spanned by the peak frequency on the horizontal axis and the total gravitational energy density or peak energy density on the vertical axis. And then each spectrum just corresponds to one particular point, which you can see here in this plot. And then in this way, I have one sensitivity curve, but I can compare hundreds or thousands of different benchmark points and dozens of different models to each other. So this really gives you a global perspective on the sensitivity of future experiments. Unfortunately, the conclusion here is that we have to be lucky to actually see something with LISA. So these are all the models that have been studied by the LISA Cosmology Working Group and all the benchmark points that they studied. And among those benchmark points, it's some percent fraction, maybe 5%, that will be within the sensitivity reach of LISA. So yeah, we have to be lucky to actually see a signal, or maybe we have to hope that there was a different kind of phase transition that will give us a stronger signal. Okay. Well, in this list of models here, spontaneous B minus L breaking is not included, and that's just because at the moment there is no such comprehensive analysis of the parameter space of spontaneous B minus L breaking. What exists in the literature is the following. So let me just give you an overview of works that have appeared in the literature. Those Japanese authors, for instance, last year, roughly a year ago, they studied the minimal B minus L extension of the standard model. So that just consists of an additional vector boson, the B minus L vector boson, a complex scalar phi that breaks B minus L, and the heavy neutrinos N1, 2, and 3. And then those Japanese authors, they study 3 benchmark scenarios. And then you can think of this as a point, as a proof of principle. So they look at just 3 points. I mean, in this plot, this would correspond to 3 individual points. So they show that with those benchmark values, you can actually get a signal that's within the reach of LISA or the SIGO or Cosmic Explorer. And in agreement with what I said on the previous slide or 2 slides ago, you have to consider a rather low value of the B minus L breaking scale. So here you're in the range of a few TeV or maybe 1,000 TeV, but certainly you're still far away from the scale of leptogenesis or grand unification. Okay, there have also been studies of non-minimal B minus L extensions, including more scalars in the scalar sector. And then there have also been studies of B minus L breaking in the MSSM, the minimal supersymmetric standard model. Okay. Well, it can even be more minimal if you make an extra assumption. Keep in mind how the scalar potential looks like in this case. Now we can basically throw away the B minus L scale in the scalar potential if we assume that the classical Lagrangian obeys or respects a scale invariance. Yeah. So the idea is to assume classical scale invariance in the Lagrangian, so there are no mass scales at tree level. And then the scalar potential reduces to this form here. So we just retain the quartic couplings, and that has been studied by several authors that I list here in these papers. Okay. The idea in this case is that symmetry breaking occurs via the Coleman-Weinberg potential. So it's something that happens radiatively at one loop order. Okay. A consequence, maybe also, well, yeah, you could say an advantage of that is that you end up with a large amount of supercooling. That means the phase transition itself is very slow, a very small value of beta, and it's very strong, so a very large value of alpha. That gives you a strong signal. A caveat here in this case is that such large values of alpha, such strong phase transitions, have not yet been simulated in numerical simulations. So to arrive at those predictions, you actually have to take the numerical simulation results and you have to extrapolate them across many orders of magnitude in alpha. So that should be taken with a grain of salt. Now, these Japanese authors, they studied the B-L phase transition in this conformal extension of the standard model, and they performed a Fisher matrix analysis, which you can see here in this plot. So they show that LISA could still probe values of the B-L breaking scale up to 10 to the 7 or 10 to the 8 GeV. In the plot, the B-L breaking scale is just this parameter m hat. Okay. So the conclusion of this part of my talk is that these are promising results. It would be exciting to see such a signal in gravitational waves, but they are also still far away from the energy scales of vanilla leptogenesis and grand unification. I mentioned that for vanilla leptogenesis, you would like to go up to 10 to the 9 or 10 to the 10 GeV, and grand unification is something that happens at 10 to the 15 or 10 to the 16 GeV. So the next natural question is, how about even larger values of the B-L breaking scale? What kind of signal can we hope to see if B-L should be much larger than, well, for instance, this number here, 10 to the 8 GeV? And that brings me to the second part of my talk, gravitational waves from cosmic strings. Right, okay, so let me begin with a brief summary of cosmic strings. Cosmic strings in a nutshell. Those are those topological defects that you produce when you break a U1 symmetry in the early universe. And that's something you can also put on the computer and then simulate. I found this nice picture here by the Cambridge group on their webpage. And what you find in those simulations is that, well, there will be a network, or there will be a population of infinitely long strings. In this picture, those are those wiggly lines that you see there in the simulation box. Okay, but in addition, there will be also string loops, and then this is what looks like those grains of dust in the simulation. Okay, so this will be a network of long strings and string loops, and together those long strings and string loops, they will reach a certain scaling regime. That's also something that you see in the simulations. The energy density of the cosmic string network will just scale like the background energy density. So the fraction in energy, the energy fraction of cosmic strings will remain constant during the scaling regime. Now, cosmic strings radiate off gravitational waves. Okay, and the most important source are the cosmic string loops, actually. So along those loops, you find certain features that propagate along the loops. Those are those, this is what is referred to as kinks and cusps, where the tangent vector along the cosmic string loop does those funny things. And then cusps, they can emit gravitational waves. Kink radiate off gravitational waves. And also kink collisions can lead to gravitational waves. So it's mainly the cosmic string loops, not the long strings, that are responsible for gravitational waves. Now, if you want to simulate the evolution of this cosmic string network on the computer, you have basically two choices. And there has been a debate in the literature for the last 20 years or so, and it's certainly still an ongoing debate. So people have certainly not reached a conclusion yet at this point. One approach is to say, okay, compared to the expanding universe and the Hubble radius, I can I can approximate my cosmic strings to be infinitely thin, okay, and then you would say you can describe them by the Nambu-Goto action. So my cosmic strings are purely one-dimensional objects. In this case, I don't talk about particles, particle degrees of freedom. So cosmic strings will just lose energy into gravitational waves. There will be no particle emission. The alternative approach is to study cosmic strings in the abelian Higgs model. So, and in this case, you don't forget about the fact that those cosmic strings belong to a quantum field theory. So you take into account your massive gauge boson degrees of freedom and massive Higgs degrees of freedom. And then what turns out is in the simulations, you see how your cosmic string loops actually decay into these massive particles. That's kind of unexpected because you would think that this decay mode should be suppressed the heavier those degrees of freedom are. But this is what you observe, and then this leads to a very short lifetime of your cosmic string loops. So they're basically gone within a Hubble time, and then in this case you lose this strong source of gravitational waves. As I said, this is still an ongoing debate, and then the following I will take the same approach as the LISA Cosmology Working Group, and then well, those folks, they're just being optimistic in this paper, and I think that's totally fine. I also want to be optimistic in what I'm going to present on the next few slides. So let's be optimistic and then say, okay, we base our analysis for now on Nambu-Goto strings, and then we can hope to see a stronger gravitational wave signal than in the abelian Higgs case. Okay. So let me become a bit more specific now and talk about a particular model. That's something that we worked on already 7 years ago, and then that goes back to even earlier work, 10 and 9 years ago. That's a minimal supersymmetric model of B-L breaking in the early universe. And then the idea is, well, to write down this superpotential and supersymmetry. That's what you would write down if you want to break a U1 symmetry. The symmetry breaking field is contained in those superfields S and S bar, okay? And then they will acquire this symmetry breaking VEF, VB-L here, okay? But if you look at the superpotential, you see that there's additional superfield, this chiral field T out front here, and then you realize that's the same superpotential that you use to construct supersymmetric hybrid inflation. So this minimal supersymmetric model can accomplish B-L breaking and inflation. And hybrid inflation basically means that inflation takes place in a two-dimensional scalar field space that's shown in this plot here on the upper left. Okay, so during inflation, the inflaton field that's contained in T will slowly roll down the scalar potential. Okay, but then there's this orthogonal direction which is contained in S and S bar. Okay, and then during inflation, this orthogonal direction is stabilized. But then once the inflaton field reaches a critical point in field space, the orthogonal direction will get destabilized and will transition from the false vacuum into the true vacuum. And that's nothing but, well, basically a phase transition, a second order phase transition. In the context of hybrid inflation, that's usually referred to as the waterfall phase transition, a second order waterfall phase transition. And the advantage here is that you can use that property of the model to make contact between cosmology and particle physics. You can identify this phase transition at the end of inflation with a symmetry breaking phase transition in a grand unified scenario. And that's actually what we do. So we say this waterfall transition at the end of inflation corresponds to the spontaneous breaking of B-L. And then, well, in this series of papers down here, we perform an in-depth study of the scenario, and we can show that this leads to successful reheating and successful leptogenesis via this decay chain. So our symmetry breaking field S decays into heavy neutrinos, and the heavy neutrinos decay into lepton Higgs pairs that reheats the universe and generates a lepton asymmetry. Okay. What's interesting here is to achieve successful inflation, we have to choose a very large value of the B-L breaking scale. So now finally, we reached the scale of grand unification. We put VB-L somewhere around 10 to the 16 GeV. And then in this paper 7 years ago, we calculate for the first time the gravitational wave spectrum from cosmic B-L strings. And we are trying to be careful because we compare the predictions of the Nambu-Goto strings and the abelian Higgs strings. And then as you can see, the prediction from the abelian Higgs strings is much more pessimistic than in the case of the Number-Goto strings. Okay, so this is what happened 7 years ago, and now fast forward to summer last year. In this paper here that appeared in last summer, Hitoshi Murayama and collaborators, they took this basic idea and embedded this into a bigger picture. Yeah, so they performed a more general analysis of a certain class of minimal grand unified scenarios. That's what you can see here on the upper left and in this plot. They consider grand unified scenarios that all start with an SO10 gauge group, and then they consider different symmetry breaking patterns. What they find is that in many cases you have a post-inflationary phase transition that leads to the production of cosmic strings. Okay, so that's kind of a generic outcome that you would expect in many models. So then the question is, what kind of gauge group do you break your gut group to in the end? They distinguish between two cases. It could be that you retain a Z2 meta parity at low energies. Maybe that's necessary or that's useful if you want to include dark matter into your model. Okay. It turns out that this Z2 meta parity is actually a subgroup of the Z4 center of your SO10 gauge group. So in a sense, this meta parity is still part of the is an unbroken part of the initial gut gauge group, and that can protect the stability of your cosmic strings. These are all the 3 blue arrows in this plot here on the upper left that go to a G-standard model cross Z2. Those are stable Z2 symmetry protected cosmic strings. And there's this other blue arrow that just goes to the standard model gauge group. Okay. And then that happens, this is the case when you don't retain meta parity at low energies. And then you end up with a network of unstable cosmic strings. They can decay because in the original SO10 theory, you can't have stable cosmic strings. They will just decay into pairs of SO10 monopoles and antimonopoles. Okay, and Hitoshi and collaborators, they also estimated the gravitational wave spectrum, assuming a Number-Goto strings. And then what you can see on the upper right in this plot, that's very, well, yeah, that's again very optimistic. I would say that values of the B-L breaking scale of order 10 to the 15 GeV are already in tension with existing PTA bounds. But what they find is that values between 10 to the 10 and 10 to the 14 GeV are still consistent, and then would give you an observable signal in gravitational waves. Okay, so now you may think, wait a second, how is this possible? You say 10 to the 15 GeV is in tension with existing PTA bounds, and on this slide you showed us your model that uses 10 to the 16 GeV. So what's going on here? That's a question we ask ourselves again in last December. So that's basically a follow-up to the previous papers in collaboration with Hitoshi. And then, yeah, people at DAISY in Hamburg. Okay, and we basically revisit our minimal supersymmetric model. I don't have time to go through this very complicated plot here. So this includes really a lot of information. I can't go through this entire plot. Let me just say, this plot shows that there's a viable regional parameter space, and that's consistent with everything that we want to include into our model. So in this viable green region, we get successful hybrid inflation. That works. Everything is consistent with the Planck data. We get reheating, independence of our neutrino and Higgs parameters. We can realize leptogenesis. It's a combination of thermal and non-thermal leptogenesis, and we can even produce dark matter. That's again a combination of thermal and non-thermal production chains. Okay, but what sticks out here is that this viable part of parameter space again gives us a very large B-L breaking scale, something between 3 times and 6 times 10 to the 15 GeV. And then, well, we can have a look at this plot here. Well, if you include a line for a few times 10 to the 15 GeV, this will reach those existing PTA constraints. I mean, in this plot, you see the bound from the nanograph collaboration, but there are also constraints from the PTA and the EPTA, the European pulsar timing array, and so on. Yeah, so what we find is our model is very nice because it gives you inflation leptogenesis and all that, but it's in conflict with existing PTA bounds. So how can we solve that problem? Our answer is, well, to look at this possibility of decaying cosmic strings. So the idea, and this is what I mentioned 2 or 3 slides ago, is to embed our theory into SO10, but we have to make sure that matter parity is broken at low energies. And to accomplish that, we write down this superpotential to generate the right-hand neutrino masses. So now our B minus L breaking field carries B minus L charge 1 and not 2, as in the previous case. And because of this new charge assignment, there's no matter parity at low energies, and we end up with an unstable network of cosmic strings. You can actually estimate the lifetime or the decay rate of those cosmic strings, and that's shown here. The decay rate depends on 2 parameters. One is mu, that's the cosmic string tension, energy, the dimension of this quantity, right, is mass dimension 2, and we work in Planck units here. Okay, and kappa is a quantity that quantifies the ratio of the monopole mass, the mass of those monopoles that you create when you start destroying the cosmic string network, and again the cosmic string tension. Okay, the monopole mass is proportional to your SO10 breaking scale, and the cosmic string tension is proportional to the B minus L breaking scale. So what we require is a slight hierarchy between the SO10 and the U1 breaking scales. If we put this parameter square root of kappa to a value around, let's say, 7 or 8, then we can make the cosmic string network decay at just the right time. And in this case, we will still have an observable signal, a flat plateau at LIGO and LISA frequencies, but the signal will decay off at lower frequencies, and we can avoid the existing PTA bounds. In principle, this could also give us a very nice observational signature. So for instance, if in an PTA experiments you see this rising spectrum with a spectral index of 3/2 at low frequencies, and then you see a flat plateau at high frequencies, this could be evidence for gravitational waves from a decaying cosmic string network. We can also have a look at the plot here on the right-hand side. Here we see that there's this viable region in parameter space where we can do inflation, leptogenesis, and dark matter. That's this gray shaded band. And then if we choose the right value of square root of kappa, so if we make the cosmic string network decay at the right time, then we can avoid the existing bounds, but we can still achieve a gravitational wave signal in future experiments. Okay, so I see it's 12:30 already. How much time do I still have? We started maybe 2-3 minutes later, right? Xunchan, is anybody still around?
Oh yeah, sorry, I mute myself. I forgot to unmute myself.
No worries, no worries.
Don't worry, everybody is around. You usually have 2 or 3 minutes.
2 or 3 minutes. Okay.
Yeah, in principle, you can use you can keep talking, but then audience.
No. So let me just give you a teaser of what else I still wanted to talk about, because this is a kind of new topic now. And then if people are interested, we can talk about this during the coffee break or whenever. I just want to, well, mention the main idea here, and then I will skip to my conclusions. All I said so far is based on the idea of supersymmetry, and then you can ask this blasphemic question: what if there is no supersymmetry? Could you believe that there's no supersymmetry? Okay, so what happens then? And then you run into the so-called Visani bound. Okay, this has been worked out by Visani in the 90s. Okay, the point is that in the type 1 seesaw mechanism, if you make your heavy neutrinos very heavy, as heavy as we had them on the previous slides, then one loop threshold corrections from the heavy neutrinos to the Higgs sector will lead to very large radiative corrections to the Higgs mass. Okay, and that leads to a hierarchy problem or a naturalness problem. If you want to avoid this naturalness problem, then that's what Visani said. You have to, then you have to satisfy an upper bound on the right-hand neutrino mass of roughly 10⁷ GeV. Okay, but this again is then well, this is not what we considered in the previous model, because there we wanted to have everything at the high energy scale, close to grand unification. So what we did in a recent paper is to look at the following very interesting scenario. So we consider a very weakly coupled B minus L breaking scalar field. So we say, okay, the B minus L breaking itself takes place at a high energy scale, and that's motivated by grand unification. Okay, but then we assume that the scalar field is very weakly coupled, it has very small Yukawa couplings. So the masses in the heavy neutrino sector that it introduces or induces are still very small, comparatively small. So we choose very small couplings so that the neutrinos themselves have masses below 10 to the 7 GeV, below the Vazani bound, because that's motivated by electroweak naturalness. Okay, and if you make this assumption, if you assume a very weakly coupled scalar field, then it can be very long-lived. It could drive the expansion of the universe, could be the dominant form of energy in the universe. And what we find then is that there could be an extra stage of early matter domination in the early universe just right after B minus L breaking. So there could be a scalar era after B minus L breaking that would lead to a characteristic break in the gravitational wave spectrum. You can see this here on the top right. The gravitational wave spectrum would fall off with a spectral index of -1/3. We could also talk about this later if people are interested, but that's what we find. Okay, and then if you should be able to observe a flat part of this plateau, a flat part of the spectrum, the break, and then the decrease at higher frequencies, this would allow you to basically test the scenario. Let me just jump to those plots here. If you can see the plateau and the break, then you would be able to probe two fundamental scales. One is the B minus L breaking scale, and the other one is the neutrino mass. Okay, you can see this here on those plots, the horizontal and the vertical axis. And so what we find is that in this scenario of a weakly coupled scalar field, you could probe exactly the parameter range that's relevant for low-scale leptogenesis. And that's very exciting because it allows you to probe the right-hand neutrinos in the multi-TeV range up to the Vazani bound of 10 to the 7 GeV. And that's really kind of unique, a unique cosmological window onto this part of the seesaw parameter space, something that you would never be able to achieve in terrestrial experiments. Okay, so this is just a teaser for this paper. And now my time is up. Let me conclude. I talked about gravitational waves from cosmological B minus L breaking, and well, I consider different ranges for this parameter B minus L. If you break B minus L at a low energy scale, we can hope to see gravitational waves from a first order phase transition. Then if you break it between 10 to the 10 and 10 to the 14 GeV, we can hope to see gravitational waves from stable cosmic strings. If you go to even larger energies, then you have to assume that the cosmic strings are unstable, otherwise you will violate existing PTA bounds. And then this is what I just mentioned at the very end. If you make this extra assumption of a weakly coupled scalar field, then you can have a chance to probe low-scale leptogenesis in this range of breaking scales from 10 to the 11 to 10 to the 16. Better understand the dynamics of the first order phase transitions, especially the turbulent part. Okay, then there's this discrepancy between the number Goto and the Boolean-Higgs simulations. It's important to perform more comprehensive phenomenological scans of the parameter space. But in my opinion, this could be one of our best shots at probing new physics, or at least right-hand neutrinos and the seesaw model at very high energies. And with that, I would like to stop and thank you for your attention. Thank you very much.
Okay, let's unmute ourselves and let's thank Kai again. Yeah, we have time for two short questions. Okay, who is this?
I guess it's me. It's Laura.
Hi, Laura. You can ask now.
Thanks. So,
hi.
Hi, Kai. Thank you very much for your talk. I wanted to ask you, in the context of hybrid inflation,
Right.
Where is the, like in this model that you studied, where is the, here exactly? So where is the, is there like some interesting phenomenology going on in the tensor sector? So I'm talking about primordial gravitational waves generated during the inflation in this?
Yes, that's a very good question. That's a very good question, and so we tried to include this into an analysis here in 2013. So what you can see here in the plot, I mean, you don't see my cursor, but it's in the plot here on the top right. We include the prediction from inflation itself, and it's a kind of general problem with hybrid inflation. It's a scenario of a small field inflation. That means that inflation takes place in a small part of scalar field space. It's a very flat potential. Your slope perimeter epsilon is very small, and your tensor to scalar ratio is very small. So unfortunately, yeah, you will not be able to see gravitational waves in the CMB. Yeah. In this scenario.
Yeah, and there is not even like at short scales for some.
No. I mean, this is okay. This plot is pretty old already, and we basically redid the entire analysis last year, but the conclusion doesn't really change. And in any case, the signal. Okay, so I mean, both inflation and cosmic strings will give you gravitational waves across a large range of frequencies. Okay, I mean, those signals here, they're stretching across many orders of magnitude in frequency space, and the signal from cosmic strings will always be dominant, and then the one from inflation will be subdominant.
Okay, thank you very much.
Yeah, thank you for your question.
Okay, since we run out of time, so let's thanks Kai again and move to next talk.
Okay, thank you very much. Thank you.